गुड मॉर्निंग स्टूडेंट्स। अभी हम लोग केमिकल इक्विलिब्रियम का चैप्टर डिस्कस कर रहे थे और आज आपको मैं क्लॉजियस-क्लैपेरॉन इक्वेशन के बारे में बताऊंगी। तो क्लॉजियस-क्लैपेरॉन इक्वेशन में पहले क्लैपेरॉन इक्वेशन के बारे में बताएंगे और क्लॉजियस-क्लैपेरॉन इक्वेशन इज नथिंग बट एन इंटीग्रेटेड फॉर्म ऑफ द क्लैपेरॉन इक्वेशन। तो क्लैपेरॉन इक्वेशन एक्चुअली कहाँ पर हम लोग लागू करेंगे इसको? फेज रूल में भी हम लोग लागू करते हैं, थर्मोडायनेमिक्स में भी यूज होती है, इसके एप्लीकेशंस हैं। तो ये एक्चुअली हम लोग कोई प्योर कंपोनेंट अगर लेते हैं और उसके दो फेजेस जब इक्विलिब्रियम में होंगे, सपोज द सिंपलेस्ट केस इज वी टेक वाटर। ओके, अगर हम लोग पानी लेते हैं, वाटर लेते हैं, तो उसके कितने सारे फेजेस होते हैं? आइस होता है सॉलिड फेज, लिक्विड होता है वाटर होता है लिक्विड फेज, और वाटर वेपर होता है इन द गैसियस फेज। तो ऐसे इक्विलिब्रिया, प्योर कंपोनेंट के इक्विलिब्रिया जो कि डिफरेंट फेजेस जो कि इक्विलिब्रियम में हो, प्योर कंपोनेंट के डिफरेंट फेजेस जो इक्विलिब्रियम में हो, वहां पर हम लोग स्टडी करेंगे आज क्लैपेरॉन इक्वेशन। उसी ऐसे ही सिस्टम्स के लिए हम लोग आज डिराइव करेंगे। तो यहाँ पर हम लोग देखते हैं कि अगर फेज ए है और एक फेज बी है, ओके, फेज ए है फेज बी है और ये प्योर कंपोनेंट के फेज ए फेज बी है और ये इक्विलिब्रियम में। ओके, तो कितने तरह के वैसे इक्विलिब्रियम पॉसिबल हो सकते हैं? ये मैंने यहाँ लिख रखा है, सॉलिड एंड लिक्विड, liquid and vapor is possible, solid and vapor is possible, and there can also be allotropic equilibrium, allotrop of 1 with allotrop of 2, and all these are for pure components. तो अगर हम ऐसा सिस्टम लेते हैं, फेज ए इज इन इक्विलिब्रियम विद फेज बी, तो यहाँ पे जो हमारी मोलर फ्री एनर्जी होगी जिसको हम लोग कहते हैं जी, तो जी ए, सपोज वी आर टेकिंग दिस इज फेज ए इज इन इक्विलिब्रियम विद फेज बी. Now what will happen? When it is in equilibrium, suppose this is the molar free energy of phase A and this is our molar free energy for phase B. Then at equilibrium what will happen? At equilibrium GA will be equal to GB. The molar free energy of phase A will be equal to the molar free energy of phase B. Okay. Now suppose we make small changes in pressure in this phase A and phase B, small change in pressure. Let initial pressure be P and T, and suppose we are making small changes in pressure. So what will happen? The pressure will become P plus dP. Now to counteract the change in the pressure, the temperature will also change. The temperature of the system will also change. Let it be T plus dT. The temperature changes. There is a small change in the temperature, and let it be T plus dT. So our new pressure is P plus dT, and our new temperature is P plus dT. So when these changes occur, obviously the molar free energy will also change. And what will be the new molar free energy? Ga plus dGa, means small change in the free energy is equal to Gb plus dGb, and this is happening at equilibrium. Okay, since we have changed the pressure and as we have stated the initial principle that the system will try to attain the equilibrium, there will be change in the temperature and our molar free energy of these two phases will now be this. Now we have seen that Ga is equal to Gb. So when Ga is equal to Gb, means the change in the free energy will be equal to 0. Okay, so when Ga is equal to Gb, when Ga is equal to Gb, then obviously dGa will be equal to dGb. Now we have studied a very relevant thermodynamic equation, that the change in the free energy, let me write it here. Change in free energy is equal to VdP minus SdP. Now here you all know that dG is the change in the free energy, small change in the free energy, B is our volume, dP is a small change in pressure, S is the entropy, molar entropy. We are talking about the molar volume and the molar entropy, and dT is the change in the temperature. Now when we apply this equation for phase A, what we get is dGa will be equal to VA into dP minus SA into dG. Similarly, for phase B, dGP will be equal to how much? VB into dP minus SB into dt. Now we are having these two equations, but dGA is equal to dGB. This means we can equate both of them. So what we get is VB into dP, VB dP minus SB dt will be equal to VA dP minus SA dt, because dGB is equal to dGA, or you can say dGA is equal to dGB. I have written it in this reverse form so as to avoid the negative sign, because afterwards we have to cancel it out. So we have this equation now. Okay, so let me mark it as equation number 1. Let this be equation number 2, and let this be equation number 3, and let this be equation number 4, and this is 5, and this is 6, and finally this is our equation number 7. Okay, this is our equation number 7. VB dP minus SB dt is equal to, this is for phase B and this is for phase 1, and since dG is equal to dGB, so we are at this equation number 7. So now let's keep the dP terms on one side and dt terms on the other side. So what we get is VB into dP. This is our another dP term minus VA into dP is equal to, we take this to that side, so it will be SB into dt minus SA into dt. Let it be equation number 8. Now we see that dP is common over here and dt is common over here. So we can write it in this form: VB minus VA into dP will be equal to SB minus SA into dt. Equation number 9. Now a slight of rearrangement over here in this equation number 9, and what we get is dP upon dt will be equal to how much? This is dP upon dt will be equal to how much? SB minus SA. SB is the entropy of the phase B. VB minus V. So this comes out to be SB minus SA. Okay, SB minus SA. Suppose we have taken water in it, so let this be the water system and this be the water vapor. Okay, so this will be SB minus SA. We are giving heat to it, and water is converting to the vapor form. Okay, in this system we are supplying heat and water is getting converted to the vapor. So this will be dP upon dt will be equal to delta S upon delta V. Okay. So dP upon dt is equal to delta S upon delta V. Now we will apply second law of thermodynamics over here, which says that the change in entropy is given by, from second law of thermodynamics we have that the change in entropy is given by the heat absorbed during the reversible process divided by the temperature at which it is being absorbed. Okay, we will now apply this equation, the value of delta S from here, and we will replace the delta S value with this factor Q upon T. So what we have it, dP upon dt will be equal to delta S is how much? Q upon T. So it will be Q upon T into delta V. And what is delta V? Delta V is the change in the volume. Okay. Suppose we are having the two phases are liquid and the vapor, then the change in volume will be the volume of the vapor minus the volume of the liquid. Okay. And as we all know that in case of water, the volume of the liquid is very small compared to the volume of the vapor. Okay, that I will tell you later on. So we are having this thing. Now this is what Q reversible means, heat absorbed at during the reversible process. This we have arrived from the second law of thermodynamics, which says that the change in entropy is given by Q upon T. T is the temperature, liquid. So this is our, here we have that, suppose we are having this system, solid is changing to liquid. Then at this point what we have is latent heat of fusion, which we denote by HF. Okay, and here when liquid is changing to vapor, we have the latent heat of vaporization. And here we solid is changing to vapor, we have the heat of sublimation, and when isotropics are changing, then we have the transition, heat of transition. Okay, so here when we are taking the liquid and the vapor, then we can write it in this form, that dP upon dt means the variation of vapor pressure with temperature will be equal to how much? Delta HV. Okay, HV means latent heat of vaporization, because we have the two phases we have chosen here are the liquid and the vapor. So it will be the HV upon T into volume of the gas minus volume of the by gas I mean water vapor of the liquid. And since in case of water the volume of G is very large compared to Vl, so we can neglect this thing. So what we get is HV upon T multiplied by volume of the vapor. So dP upon dt will be equal to this. So this is our one form of the Clausius equation. 9 let it be 10 and let it be 11. So this 11 and as well as 10 we can say as 10 also, and no, this is 10, let it be 11, let it be 12. So 11 and 12 they represent our Clapeyron equation over here, and we can see what it signifies is that the change of vapor pressure with temperature. This value will be a certain value at this temperature. Suppose this T is changed, then the value of dP upon dt will also change. Now suppose we were taking it not for this equilibria, for the liquid and the vapor equilibria, suppose we were taking it for solid and liquid equilibria, then what would have been the equation? That the equation would have been dP upon dt is equal to HF, the heat of fusion, divided by T into the volume change. Okay, it is a G, then we can consider volume of the solid, volume of liquid minus volume of solid. Okay, so this is our Clapeyron equation, and this Clausius-Clapeyron equation is nothing but it is the integrated form of the Clausius equation. So now I will tell you about the this equation, Clausius-Clapeyron equation, by doing the integration of this factor. Okay,